In this tutorial, I would like to show you why the RMS average load calculation is important for the selection of many systems, in particular of motors. We will outline how to calculate this root mean square or RMS value. In motors, current is needed to generate torque. The motor current is one of the most important reasons for motor heating. Running the motor at a constant load will heat it up, due to the resistance of the winding. The temperature increase follows an exponential curve and will eventually reach an equilibrium value. At the lower absolute current load, the resulting end temperature will be lower. It doesn't matter that the current flows in a negative direction, the heating is the same. The maximum permissible temperature defines the maximum permissible load current, or nominal current. If the current is even higher, the resulting temperature increase exceeds the maximum permitted value. Accordingly, the time duration for this overload is restricted. What happens to this general picture if the load is not constant? Let's assume an operation cycle consisting of 4 load phases T1 to T4 with different current levels I1 to I4. As you can see, during phase 1 the current is higher than the maximum permissible current, while the current in phase 4 is 0. Overloading the motor in phase 1 is not critical, as long as the overload current is not too high and the duration is short enough compared to the thermal reaction time of the motor winding. And that's typically at least several seconds. The question that arises is, what will happen to the temperature if we want to constantly repeat this operation cycle? During the high load in phase 1, the temperature will increase strongly, while in phase 2 and 3 the thermal load is smaller. In phase 4 the motor has time to cool down since there is no current. However, repeating this cycle permanently will heat up the motor. In the end, the motor temperature will vary slightly around an average value. It's this average end temperature we're interested in. And, as we have seen, corresponding to the average temperature, there must be a permanent current value that generates the same average heating. This is the meaning of the RMS current. It's the mean current value that creates the same temperature increase as permanently repeating a given operation cycle. Observe. The RMS value describes the steady-state behavior. It gives no information how the heating process takes place or how large the temperature variations are within the operation cycle. How to calculate the RMS value? We note, motor heating is independent of the direction of the current, and the joule power losses in the winding go with the square of the current. Hence, phases with high currents, for instance in phase 1 of our cycle, will contribute more than proportionally to the heating. All this leads naturally to the rule how to calculate the average load that represents the heating of the motor. Take the square root of the mean value of the time-weighted current squared. That's the meaning of root mean square. When is the RMS value of importance? The required RMS torque is a key load parameter characterizing the application and needed for motor selection. The typical procedure for RMS load torque evaluation is as follows. First, evaluate all load torque values for the different phases of your operating cycles. Consider friction and acceleration forces as well as constant forces such as gravity. Multiply the duration of phase 1 with the square of the torque in phase 1. Repeat this procedure for all the operation phases and sum up all the values. Then divide this sum by the total time of the operation cycle, including dwell. At the end, calculate the square root from this result. For motor selection, the RMS torque value must be smaller than the maximum permissible continuous or nominal torque. That's the right limit of the red continuous operating range. That's it. You should know now that the RMS load value gives the average thermal load for operation cycles. and that the calculation goes just as the name indicates. Take the root of the mean value of the time-weighted square load.